it's my distinct pleasure to introduce Dr. Kunduri. Dr. Kunduri is at McMaster, and he's here with his lovely wife. Dr. Kunduri completed his undergraduate degree in physics and mathematics at the University of Toronto, and then obtained his PhD in 2007 from the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. Following this, he held postdoctoral fellowships at the Universities of Nottingham, Cambridge, and Alberta before taking up an assistant professorship of mathematics at the Memorial University in St. John's, Newfoundland. He joined McMaster University as an associate professor in mathematics and physics in 2022. His research focuses on the mathematical theory of black holes in general relativity. At Cambridge, Dr. Kunduri was on Stephen Hawking's team. Dr. Kunduri's supervisor was Malcolm Perry, who himself was Stephen Hawking's student. When Dr. Kunduri was there, Stephen Hawking would attend weekly talks, although to be honest, the students were a little bit shy around Stephen Hawking. But Stephen Hawking wanted to be treated as a normal person. Later on, in his 75th birthday conference, Stephen Hawking invited his former students over to his house, which was a modest one and not too far from the department. And Dr. Kunduri, in his free time, plays hockey for all the hockey lovers out there. So you may want to have a quick word with Dr. Kunduri at the break if you're a hockey fan. It is my honor to present Dr. Kunduri at our meeting tonight. He will speak about the unreasonable simplicity and complexity of black holes. Dr. Kunduri.
Thank you very much. I'd like to thank Swapna and Chris, who gave me a ride, Alan, all the people who helped, who invited me over here. So that's very that's nice of them. And I'm surprised there's just many people who want to hear about this stuff on a Friday night. But as someone mentioned to me, there is no Leaf game today. It's actually tomorrow. They play Ottawa, so you're not missing anything. So the first thing I want to say after thanking all of you is, I guess what I'll be talking about is a little different than maybe what you usually hear, because I'm certainly not an astronomer. I do maybe a more theoretical subject, I guess, maybe more on the ground. No, less on the ground, hang on. More fundamental stuff, and I don't even get that far. And it's always impressed me what astronomers do, really. I don't even, it kind of blew my mind. It's almost too much. And, you know, you get a feeling of awe. I guess literally it's like a predator, like a prey response, like the hair stands up because there's a cat around and you're scared. That's how a mouse would feel, right? That's how I feel when I look up at the sky. There's just too much. And how you guys, you know, understand that and deal with that, and you know, we're able to come to terms with it, I think is amazing. It's something kind of over my head. So I'll tell you what stuff which might be over your head, but I'll try to make it understandable. But this stuff is really, I'll say one thing. When I went to learn this stuff, say when I was in high school or something, I always found they never gave so much detail. It was all the mystery of the universe, fabric of this, space-time mysteries. And you can watch that on PBS. I do, you know, I watch those shows on PBS. And that's fine, but I want to give you a bit more detail. So hopefully you'll get a deeper understanding of where some of this stuff comes from. Although maybe it'll blow up in my face, so we'll see. So the reason why the topic of my talk here today is the unreasonable simplicity. So in one point of view, black holes are very simple. It turns out in Einstein's theory of general relativity. So that's the picture on the left. There's this beautiful, pristine, geometric picture where people like I work in, like me, that's where I work in, where everything is nice and simple. And then there's this horrible world of quantum mechanics where things are really complicated, complex. And that's the picture on the right. So when I'm writing sort of funding grant proposal stuff, I'm trying to say, I want to understand the stuff on the right, but I work mostly on the stuff on the left, but that's a little bit more mathematically clear what you're doing. But ultimately, they're very simple from this geometric point of view. And yet, as I'll try to explain quantum mechanically, they're very complicated. So this is why there's so many, how would I put this? Black holes are at the forefront of understanding in theoretical physics. So whenever you see work in theoretical physics, often it's related to black holes. And the reason why is because they're sort of in an overlap region. a region where you need both general relativity and also quantum mechanics, but they sort of overlap. So you can, it's at that stage, that's where all the interesting stuff happens, really at the boundary of knowledge, right? The deep end, literally the deep end, where you're about to fall off. Well, that's where all the exciting stuff is. So I just want to give a quick outline of the talk. I want to explain what general relativity actually is, heaven forbid, and where black holes fit into all this. So it's a bit of a history lesson, but I kind of like that stuff. And I think it gives a perspective on how far we've come in understanding of things. And then towards the end, I'll sort of talk about the hard stuff, which is why these things are interesting for the theoretical physicists and the high energy people. Okay, so black holes are an odd thing because they're of interest to astronomers like you. They're of interest to maybe more mathematicians, mathematical physicists like me, like some weird guy in between everything. And then there's theoretical physicists, and then there's astrophysicists, and they're all kind of fighting over the same ground, and we can't talk to each other at all. So on Wednesday, there was a talk by a professor from Waterloo, Nyashav Shorty. And anyway, he came and gave a talk on black holes. And I was having lunch with him after, and we get a free lunch because we get to take the speaker outside, join with this. And then he said, I know you've been working on it. What do you do? I said, well, black holes. He goes, that's strange. I never came across you in 20 years or something. And yeah, it's just, that's the way it is. It's a big place, black holes, and you may never meet people who work in black holes. And maybe that's better because you don't fight about turf and this sort of thing. Okay, well, that's true. Like, I don't want to talk about physicists doing this stuff for mathematicians. I'm in my own world. And, something I wanted to say that struck me when I looked at the word astronomer, as amateur astronomers, the word amateur comes from amour, it means love, right? So it's sort of, you guys do it because you want to do it. You have a passion for it, and you're not interested in the outcome just because you're interested. That's the best stuff to be doing. So let me see here. So before I get into that, this one more philosophical comment, which I like. So I often like to tell audiences, when I give a general audience, we use words like beauty and love. This is a beautiful equation, blah, blah, blah. What does this mean, actually? And to someone who studies mathematics or physics, I don't know, it's a hard thing to explain, I guess. But the best way to explain it is, I think, through music. So here I've written something. So if someone you know how to play music would recognize that. I mean, not me. But if I described it in words, I said, well, it's in the key of C sharp minor or something. Who cares? And it's in this key signature and it's in this time signature. Why would anyone care about that, right? But actually, it's sort of like that's what it is. That's the knock on the door. Let's see here. Let me see. So it's Beethoven's Fifth Symphony is, the opening notes to it. And so the reason why that is beautiful is because it's not just the individual notes, but sort of where it all fits together. In the bar, in the symphony, in his masterworks, his opera. I'm sorry, I'm mispronouncing the word opera here. So all these things, where it fits into classical music, and it's the branching point between classical and romantic periods, and all this stuff, and you just look at that and you see the beauty. So unfortunately, with mathematics, you can't really, the beauty isn't, I can't describe it, right? It'd be like if you're listening to music and the person described it with words. And now they're going up into this note, now we're doing this. Like, who would listen to that, right? No one in their right mind. So we can all appreciate music, but maybe mathematics is a little harder to see. But there is a sense of beauty where things fit together nicely. And that's what we mean when we see something's beautiful. And general relativity is like that to people who work in this because it just fits together beautifully. Unfortunately, it seems like there's some issues with it and people are always trying to screw it up. The people like me who are kind of purists don't want them doing this, so we're always arguing with them. And, but things can be wrong. And even a genius like Einstein, that doesn't have to be the end of the world. There could be more to come. And that's a good thing for the rest of us. Okay, so that's my rant on this stuff. So the first thing I want to talk about with you guys is what relativity is. So as I explained to students, even students in my class who are taking a relativity class with me this year, McMaster, there's nothing about relativity that has to do with Einstein. Actually, people like Galileo knew about this, and even Newton, a little bit after Galileo. So the idea of relativity is just, there's different reference frames. There's me, there's you, right? And say I'm moving relative to you, then The idea is if I do an observation or experiment, I want to be able to compare what I get to what you get. And we should be able to compare the two things. And, from you can see what I'm seeing and I can see what you're seeing. It's like a way to map between different observers. Okay, that's what relativity really is. So here's a really simple example. Someone is on a train moving at some speed v, right? And if they throw a baseball, okay, so they throw a baseball, then if I'm watching the train go by, probably if I measure the speed of that ball, it should be the speed of the train plus the speed that I threw the ball at. And you just add them up. It's completely common sense, right? Obviously. So that's relativity. And let's go one step further. Suppose you're in the train, I'm watching you. Okay, so you guys are moving the train past me and you shoot a light beam. So then what is the speed of light that I should see? Well, I would see the light beam moving at the speed of light that you see plus the speed of the train, right? Because say the train is moving at speed v, like 20 miles per hour. So I should see the speed of light move quicker. That totally makes sense, right? That's obviously what makes sense, except for it turns out that's not how the world works. Unfortunately, but that's how our everyday experience should work. And we do this all the time, right? So it's not a surprise. That's Galilean relativity. So then the question was, what does this have to do with light? And we come to where Einstein's theory of relativity, which came out in 1905, so it's 115, like 110 years old now, 120 years. Yeah, it's getting bad. It's getting bad. So I like this picture of Einstein because he's sort of younger and he looks worried because he's looking for a job, probably, which we can all feel, especially if you're an academic. I like that. I like that because now when you see pictures of Einstein, it's got the clown nose and the crazy hair like this and the whole thing. I like this one because he looks kind of nervous and serious. Okay, and so the thing is, everyone expected that the rules of relativity as laid out by Galileo worked until, this is the late 16th century. Galileo was working on this stuff. And then Einstein comes along and they realized around the same time, in 1850 or 1860, there was someone named Maxwell. Some of you who did physics would remember him, or engineering. He discovered the equation that described electromagnetism. Okay, so those are Maxwell's laws. So that's good for him. And Maxwell realized, if you look at the equation, you can see that light is a solution of those equations. So you say, hey, there's a solution, and it describes a wave, like those waves hitting my eyes right now, hitting your eyes. And you can check the speed in the equation. It turns out the speed is exactly what the speed of light was. So then people realized, okay, you know what? Maybe light is actually an electromagnetic disturbance. And now we understand it's like electrons shaking. As they shake, they accelerate, and they produce light. That's what light is. It's an excitation of the electromagnetic field. So good for you. Okay. So then someone said, okay, so yeah, you get this because you guys are real astronomers. So say the Earth is moving and we see a star, far away, distant star, it shines the light at us. Then as we move towards it, presumably we measure the speed of light from that source. It should be kind of faster. Then later on in our orbit, say like now where the Earth is moving away, then the speed of that light should be slower, right? So it's like quicker. Okay, I got that mixed up. As you move towards it, it should be quicker. As you move away, it'll look slower. Just because my example of the train. The difference is now like we're in the train and source is kind of stationary, but hopefully that kind of makes sense. You should see the speed of light change as we move relatively towards or relatively away from the source. Makes total sense. Guess what? People did this experiment, like Michelson and Morley in the 1880s, and then it turned out that wasn't true. So it looked like light was fixed. The speed of light seemed to be the same for everybody. Okay, so what? So Einstein came up with the idea that Galilean relativity still made sense. You can still use the laws of physics of Newton and so on. You need a kind of special rule. And the extra special rule you need is that the speed of light doesn't change. Speed of light is the same for everybody. Okay, so even if like you shine a light beam, okay, here's a light beam, and then Usain Bolt is running towards you. Usain Bolt is still going to see that light approaching him at the same speed as me. Like I'm walking as fast as I can, this fast. It doesn't matter how fast we move towards the source. The speed of light that we observe is always the same. So that's very odd. And it turns out you can write down equations to describe that. And that is what special relativity is. Okay, so the word special means, well, I'll try to explain it, but it has to do with how you relate the observations of different observers, okay? And there's no gravity involved. So that's kind of what Einstein meant by special, because he ignored gravity in 1905. Okay, so after 1905, he publishes these great papers, and then he started to think about gravity. Now, why would he think about gravity? And I'll kind of explain this. Yeah, you guys are smart audience, you can figure this stuff out. So, yeah. So the kind of observers that Einstein was thinking of were people who move relative to each other at constant speeds. Okay, so I'm here, and you move at a constant speed with respect to me. That's fine. So he was interested in the rules that govern how we relate our different observations, different reference frames. That's special relativity. So then he said, well, what happens if someone was accelerating? Right, so he wanted a general theory. So how do I relate the experiments of someone who happens to be, say, falling down and someone else who's just standing still? So now they're not related by constant velocity, but there's actually accelerations. Things are speeding up and slowing down. Okay, you've all felt this. For example, you ever felt, here's an example of where this special, like this kind of relativity idea might come into play. So say you're in a car, and then the person turns the car to the left. So you feel a force pushing you to the right. Why is that? Well, it's not like there's a hand pushing you. It's just because roughly you're in a kind of reference frame which is trying to go this way, but the car is going that way. And so you'll feel a force kind of pushing you into the sides of the car. But really the car is pushing on you this way. You ever had that feeling? It's like a G-force. You'll see the same thing when you're in an elevator. So these are the sorts of ideas that Einstein was trying to relate these relationships. Okay, so why do I have to talk about this? Well, it turned out this is really deeply related to gravity, as I'll explain in a second. Well, I'll just take a step back to Newton. So Newton already had an idea of what gravity was. So you guys have all seen this. I can't even see it myself. So you guys have all seen this. Ah, there it is. You guys have all seen these equations that describe the gravitational field. So this is why the sun goes around the earth. This is why if I drop this thing, it'll fall on the ground. Everything is great. That's why we're not all floating in the sky, because we're feeling a force. And who cares about all these expressions in here? The thing that really matters is that the equation in there that matters is the square. See, there's an r squared. And that means the force is proportional to the square of the distance between them. Okay, so the further away you go, the strength of that gravitational pull gets weaker. And you guys probably know this from all your, because you know some astronomy, you understand planetary dynamics and things. No, I'm saying that seriously. I know you do know that. I'm not joking. You guys have an intuitive grasp of that, which is amazing. And so putting all this stuff together, one thing that you'd realize, which occurred to Einstein, was that what happens if the sun just disappeared right now? Okay, like you say, it's pretty cold outside, but it would get colder, right? There's no sun. But the question is, would it happen right now? So if you believe in Newton's equation here, you'd look at this and you say, well, the light is gone, or there's no sun, so therefore the force should be zero. So, right? Because the mass, you can see the equation at the top, there's an m there. See, that's the mass of the sun. So the mass of the sun goes away, F equals zero. The thing is, if you believe in Einstein's theory, you understand that the signals travel at the speed of light, let's say. And so we wouldn't know the sun disappears until that signal reached our eye. And it turns out that's about 8 minutes. It takes about 8 minutes for light from the sun to reach our eyes on the earth. So we wouldn't know the sun disappeared for 8 minutes. The sun disappears right now, we won't know for 8 minutes. So maybe like we got 8 minutes left, guys, and now we're just going to freeze and then float off towards Jupiter or something, right? That could happen. We don't know that. So every day of your life, you should be living in existential terror. Because maybe in 8 minutes, it could all be over just like that, right? So, but you see, it's wrong then because that was incompatible with special relativity, let alone general relativity, which I haven't even got to yet. But, so there's something wrong because this is sort of instantaneous. And the really cool thing is that Maxwell's equations aren't. They are actually compatible with special relativity. That's insane. So Maxwell, when he wrote his equations down in 1860 or whatever, they were compatible with special relativity, although he wouldn't have thought of it that way. Yeah, there's people like Lorentz and Poincaré and other people who even realized this in the 1890s. They just didn't put together the way Einstein did. Okay. So anyway, that is what gravity is. So I'll tell you a little experiment that we can do now, which occurred to Einstein. One of his famous thought experiments are Gedanken, because Denken in German means to think. So Gedanken means thought. So this is one of his Gedanken experiments. So let's just think of this. So there's Newton sitting on the earth. That could be me, let's say, but not as far as Newton. I'm probably nicer than Newton as well. And so I would, if I drop this pen, I'm not going to do it because it's not mine, and probably something will happen. So if I drop that thing, it would just fall on the ground. Perfectly makes sense. That's our life. So now let's suppose we're in a rocket ship far from any planets or anything. And the rocket ship is not accelerating, just floating around in space, okay? So if I drop that ball, nothing happens, right? It'll just float around my eyes. I drop from eye height, it'll just float with me. Nothing happens, right? Let's suppose now you got a little remote control and you turn on the acceleration on my rocket ship, okay? And I don't know this. Let's suppose I'm this. And then you turn it on. Now what would happen is if I dropped, like my feet are on the ground of the rocket ship, if I drop the ball, since the bottom of the ship is accelerating up, it'll look like the ball is falling down from my point of view, which is exactly the same as gravity. So Einstein realized these two pictures are actually the same. So being in a rocket ship which is accelerating up at a constant rate, let's call it g, is the same as me dropping a ball on Earth. And one of us doing, if we drop a ball, it'll accelerate. The ball accelerates down at 9.8 meters per second squared or whatever it is. If we don't know that we're in a rocket ship accelerating up at 9.8 meters per second squared. So if you believe Einstein, there's no experiment you can do. There's no windows here. I can't see outside. Maybe we're all stepped into a rocket ship. We're all going straight up right now. But we're not. But yeah, so these are the sort of thought experiments. Einstein made that into a physical principle. He said, we can't tell those things apart. Okay? That's kind of a messed up thing. Now you could try this experiment yourself by going, say, to the top of a really tall building. Yeah, and jumping off that building. Because you're like, I'll never become a famous, I'll never be famous Stephen Hawking. What the hell's the point of this? I'll never do anything good. Anyway, what's the point? So I jump off, but because for the love of physics, I'm going to test this thing until the end. So then I could drop this pen and you'd see we'd both be in free fall because when you're freely falling, there is no gravity on you in a sense, right? Because there's nothing to push on you or pull you down. We're both accelerating down at the same rate. So if you jump off a building, you're in an elevator, say that someone cut the rope and you're just falling, it will feel like you're freely falling. There's no gravity there. So Einstein had this amazing idea that if you want to feel like how does someone move when there's no gravity at all? And he said that's freely falling, and then you should just things would move. How would I put this? As if there was no gravity. If you're really falling, you shouldn't feel that. But if you're in an accelerating frame, you will start to notice, like we do on Earth. Maybe we're in a rocket ship that's accelerating up. So now we're, in a sense, feeling the gravity, or we're feeling the rocket ship engines on us. This is like a very deep idea, which allows us to see lots of things, okay? So I'll give you one example. I know that's kind of deep. That's called the principle of equivalence. And it's a very deep idea. And if I had some equations, I've got all these beautiful blackboards. I can do that. And it's way better than I have, actually. I got like one blackboard and a whiteboard in the classroom I teach. And one of the blackboards is covered by one of these projector screens, and I don't know how to push it up because I don't know the code number. So I have all these people, I'm rolling them up and trying to hang it top. Like literally, this is my life on last Thursday. It was pretty embarrassing because I didn't have the right password. Then I had to call the person, they didn't know what to do, and people were murmuring in the class because I was losing them, and I was like, no. Anyway, so I'm glad I had help from someone who set this all up for me. God bless them, gentlemen. So so to get back to this, I'll do a little experiment that you could do in a rocket ship, which, if you believe the principle of equivalence, tells you something about how things should behave in a gravitational field. So if we were in a rocket ship right now, okay, that's accelerating upwards at a certain rate, and we shoot a light beam from the left side, right? It'll go across a straight line. That's all fine. But since it's floating, it's flying this way, the rocket has moved in between. So by the time the light beam hits that guy hits the other side of the room, it's going to hit it a bit lower than where it started. That side of the wall has moved up in between, right? It seems a bit weird. If you shoot a light beam, you should know it. So we're in this rocket ship, it'll hit a little bit lower than where it started from. And if you believe the principle of equivalence, that should be equivalent to the picture on the right. So if we're in a constant gravitational field here in this room, if we shoot a light beam from there, if we had some really precise experiment, you would see it dip down. That seems crazy, but actually that's true. And people have done experiments so you can see the light beam really does dip down. So gravity affects light. And that's not something which you would get from Einstein, Newtonian gravity, but it is in Einstein's gravity. Okay, so this is one of these really cool things about gravity. And the fact that it affects everything is another really odd thing. So I want you to think about this. If you can, could you turn gravity off? Maybe. I guess there's way less drugs that let you sort of do that now, I guess. But basically, can you turn your own gravity off? And the answer is no, right? So all of us will feel that. Every object that exists in the universe feels gravity. You can't turn it off. And that's a very different kind of force than other forces. Like say, think of an electron or a proton or anything that has a charge, right? But there's things that are neutral, like I'm basically neutral. You turn a magnet on, I'm not just going to fly across the air. But you put a magnet on your refrigerator, it sticks. Why? I don't know. I don't stick, but the magnet does. So I can see my picture or whatever on the fridge. And so you see, there are things, some forces like electromagnetism and other forces, they act on things, but things can be neutral, so they don't feel it. So in other words, you can have neutral particles. But there's nothing neutral for gravity, right? Everybody feels it. You can't turn it off. And because you can't turn it off, you can't describe it like you can with other forces. So in physics, when you want to describe how something behaves, what do? What you do is you say, well, if the particle didn't feel this force, how would it behave? Like, what would a neutral thing do? You say, oh, look, it moves in a straight line. Okay. And then say you look at an electron, you say, oh, but now the electron is bent from where it should have went this way, but now it's being bent. And you say, that's because it's feeling a force, say an electric or magnetic field. It's feeling it, right? So in order to understand how something works, it's kind of like you need to know how it doesn't work. You need to know how it acts on things that don't feel it, right? Because then you know, oh, it's like now it's being affected. But with gravity, you can't do that because everyone feels it. So there's something intrinsic about it. And that's sort of the heart of general relativity. It isn't like a normal force of physics. It's kind of, we all feel it's sort of more like the arena that we live in as opposed to something on the outside that you kind of throw on top. And that's the difference between Newton's theory, which is like something extra. There is a force, and you imagine a rope pulling you. But in Einstein's theory, it's not really like that. It's just there. So what does just there mean? Well, I'll try to explain that here. We use the idea of curvature to explain this. So what the hell am I talking about? Okay, maybe people who are watching this can't see it if you're watching this on Zoom, but you guys can see on a screen. Einstein's idea was that if there's no gravitational field, then if I drop two balls, they'll sort of move in a straight line. You see, they don't move towards each other. Kind of makes sense, right? So this is like what we'd expect in what's called Euclidean geometry. Euclidean geometry, if you take, one of the axioms, you guys learned this in high school, take two straight lines, they keep on going, they're parallel, they never meet, right? That's Euclidean geometry. Straight lines don't get together, that's it. They'll never meet, that's the end. But now when you do an experiment, say with an apple or like a sphere at home, so let's take two lines that, maybe we start here, we go up to the equator, like that. So these lines both started out straight, right? They're both going up straight to the North Pole, and what happens? They meet, they touch. So initially straight lines start to join. And that was sort of Einstein's idea of how gravity works. Gravity would cause things which, initially they're not attracted to each other, they're moving in a straight line. And then gravity forces them together. So you see, that's very naturally connected to the drawing I drew here about how we can describe that using curvature. So there's a whole mathematical language called Riemannian geometry, which is invented just before Einstein's time, like maybe 1860s, 1870s, by people named Gauss, you may have heard of him, and Riemann, maybe not so much heard of him. He died of tuberculosis at 38, so that wasn't good for him. But Gauss is quite famous. And all these people, they came up with a theory of curvature, and they weren't interested in physics. But it was Einstein's realization that, I can describe, in order for me to describe things that are affected by gravity, I'm going to think of them as really living on this curved space, just like these straight lines on my apple here, and they're going to converge or move apart from each other. Yeah, that sounds nuts. Yeah, it's true. So that's what curvature is. And if you ever take a differential geometry class, I really recommend it. You see these things. It's a beautiful subject. But actually, you have seen this. So let's suppose maybe you're flying with American Airlines and you don't want to leave American airspace, So you want to fly over the 51st state and over the 52nd state, and you're flying towards London from, I don't know, LA. You got to get away from these fires. Don't blame me, right? So you don't want to leave American airspace. Forget that. So you're going to fly over number 51 here. Of course, the joke is maybe they'd be the 11th province, right? Aha. Now that's the joke, because do they really want I don't know if Trump wants 40 million people who would be like that in California. Maybe those aren't the electoral college votes he's looking for. I don't know. But anyway, so let's suppose you when you fly to London, from LA or even from Toronto, you go over Iceland. So why are they doing this? And that's because that's a straight line on a sphere. So the airlines know all the stuff about curvature. So differential geometry is trying to understand how does curvature affect how straight lines move. Straight lines are the shortest distance between points, right? That's obvious. And Einstein's theory, particles move along straight lines. But the point is, on a curved space, a straight line isn't kind of what you think a straight line is. And the Earth is not a flat piece of paper, right? It's curved. And so when you go on a straight line, you want to minimize the distance. You don't go across the middle of the Atlantic Ocean because it's kind of fat there. You go up top because it's curved, it's kind of skinnier near the top. You go over Iceland and you come back down. Okay? So that's an amazing fact. So we do this all the time. It isn't because the airlines want you to see what Greenland or Iceland look like. It's because it actually saves them money because it's shorter. They use less fuel, so everyone is happy. You're less longer in the plane, and you don't have to leave the American airspace. Everything is beautiful. Now, I thought of another example. I was wondering what would happen if, say, someone wanted to fly to Japan. God knows why they'd want to do that. So say if you're flying from Toronto to Narita in Tokyo, this is just, I forget which AC this is. This is yesterday's flight. I'm just doing Google on FlightAware to see the path they took out of curiosity. And indeed, this is the flight. This was just like yesterday, or I guess that's not yesterday because of the time difference. 2 days ago. But in any case, you fly over Alaska and then come back down, right? You don't fly across the Pacific Ocean because that is shorter, okay? Now, and I know it seems weird. You ever look at these maps? When I was a kid, I liked this map being Canadian because this projection map of the Earth makes the Canada look really big. I also like that because Canada was so huge. Greenland is bigger than Africa, like totally screwed up. That's because the sphere is not flat. So when you try to say, no, I'm going to make it flat because I want to make it look in my atlas, my book is flat. Rand McNally says the Earth is flat, so that's the way it's going to be. If you're going to do that, you end up screwing up the distance, so your map is not an accurate reflection of true distances, right? So all these maps I'm showing you are, in a sense, not accurate. That's why Alaska isn't bigger than, the entire half of the United States or something, or Ellis Island isn't bigger than Quebec or God knows what, right? These things are not true, but I'm just trying to explain that basically the shortest distance on a sphere, you have to go over Alaska, not around the Pacific. You don't go through Hawaii, right? You go over the Aleutians and all these things. And you get to Tokyo or Beijing or wherever it is your final destination may be. Okay? So this idea of curvature is sort of familiar. So here's a picture a lot of you have probably seen. Here in the picture on the left, your left, yeah, your left. My left too, I guess. Yeah, that's my left. So we think of the moon going around the Earth. We think of the Earth as sort of bending the fabric of space-time. What does that mean? All it means is that the space-time around the Earth is curved. So imagine you take a little marble and you shoot it. If it's moving quick enough, it'll want to go in a straight line. But the thing is, the straight line in a curved geometry is actually one where it sort of circles around. That's why the moon doesn't fly away. And similarly, on the picture on the right, you've got the sun. That's a bigger blob. And that bends space. And when it bends it, the Earth going around it, it's still trying to move in a straight line. Okay, so I guess if you learn anything about relativity from this course, that everyone wants to go in a straight line. What straight means in a curved space can mean something different. Okay, so moving in a straight line can actually mean you end up moving in a circle like we do around the sun. Okay, but we're still moving on a straight line, just like anything should move on a straight line if it doesn't feel a force. Right? Okay, so I've kind of confused everybody with curvature. So what are Einstein's equations that you may have heard of? This seems far from astronomy, but I'll try to get it back to the path there. So what does this have to do with anything? Well, there's something called curvature, tells you how things are bent. And then you have stuff like matter and sources, like planets, like I just described, or the sun. So Einstein's equations, there's something complicated. They're called differential equations. You need calculus. So any undergrads here, maybe you can for undergrad class, tell me I can see. Learn some calculus, okay? It's not stupid. It's good for you. Calculus is about how things change and how to describe that using mathematics. And essentially, Einstein's equations are a kind of differential equation. Okay, and they look like this schematically. And they're dynamical. So they tell you what happens as I set things up. So a good physics problem is like this. It's like billiard balls when you're playing pool. Okay, you set up all the balls, you set up how fast they're going, and then physics should tell you what's going to happen in the future. It's deterministic, right? Hopefully. So you set all the balls up and all the things hitting, you're going to understand what happens. And Einstein's equations are like that. You set up where the planets are, you turn the clock on, and they tell you how things are going to evolve, and they tell you what the curvature will be. Okay, that is Einstein's equation. So here I've kind of shown some pictures that are not like the kind of pictures you might take of real astrophysical objects. And I'm going to ask you lots of questions about those if I get a chance. I think that's really cool, honestly. But maybe it's my turn to talk. So different things, different masses would bend space differently, right? So the Earth might bend something a little bit. I don't know, like a neutron star, white dwarf. So what a black hole does, you could roughly, it's not totally accurate, but kind of what it does, it bends things so much that even a light ray, which is trying to move in a straight line, the space is so curved, so no matter how it tries to move, it doesn't get out. It just doesn't escape. So you can imagine, like, think of the bottom of that throat. Okay, so there's that little light ray trying to get the hell out of that thing. And eventually, it's so curved that as it tries to move, it'll never kind of escape outwards. That's a kind of idea of a black hole, which in a way is not totally accurate, but it sort of gives you the idea of what that is. Okay, so you can watch Interstellar, you can watch my slides. What are you going to do? Even though I don't think that's really accurate either, okay? And the power of lava is probably not going to save us either. I don't know, maybe it would. I'm not Christopher Nolan. But in any case, what I want you to know about a black hole is that it's not about mass, okay? It's not about how heavy you are. And it's not about how small you are. It's both. It's about a black hole is what happens when you pack a lot of stuff into a small enough region. Okay. So one of the little experiments you guys maybe have done, well, I never did this, but you might have thought of this. When they launch a rocket ship off the Earth, you talk to your buddy Elon Musk, he'll set you up. And he says, oh, we're gonna send a rocket ship out there. So what he would do is you need to calculate what the escape velocity of the Earth's gravitational field is, roughly. So a little thought experiment you can do, it's very easy, just using Newtonian mechanics. You can ask, like, what is the mass and the size needed so that the escape velocity, like that's how fast you need to be going, would be such that I could never escape. So even light couldn't escape this gravitational pull. And if you do that calculation, you get this little formula. Right, so this is a famous formula. It's like R. Forget the real factors. I'm a math guy, so I set everything equal to 1. Okay, so in my language, that's R is equal to 2m. So that's roughly the size that an object has to be for a black hole to form of a given mass. And that just seems to be like, who cares? Well, let me give you an example of what that would have to be. In fact, let me jump to here. Yes, that's a good one. If the Earth was a peanut. So if the Earth was the size of a peanut, say 1 centimeter, we'd become a black hole. Yeah, so the thing is, the Earth has got a lot of mass, and it's pretty massive, and it's hard for us to lift it, right? But even Atlas, mighty Atlas, holding the heavens from the Earth, even he would have trouble with that. So as you hold up that Earth, it's so massive, but it's still pretty big, I guess, all things considered. We're killing each other over it, but, there's enough space for us all, hopefully, if we can sort it out. And so this idea of what black hole is, a way to understand it, it's about a lot of mass being packed in a small amount of space. Okay, and so if the Earth was the size of a peanut, we'd become a black hole. For the sun, that's about 3 kilometers. If you take the mass of the sun, the size that the sun would have to be to become a black hole is around 3 kilometers. If you squish that sun down to 3 kilometers, that's still pretty big. Then it would become a black hole. Okay, so and this idea, I know this is a little funny slide here, but this idea actually refers to someone named John Mitchell. So even in the late 18th century, he sort of did this thought experiment about coming up with an object whose gravity was so strong even light couldn't escape. And turns out this is in some book I read about this, that he actually he wrote this formula down. The interesting thing is in general relativity, you get the same formula. It's a bit of a fluke. There's reasons why, but turns out it's the same formula holds. You get the same expression. Okay, so I'll skip all these equations. So what about real black holes? Well, there are real ones. And the picture on the bottom is, so the first way people came up with indirect evidence that black holes could exist, an object like this. And the picture they came up with was, they were looking at the orbits of stars. So yeah, you guys are the orbits of stars people, not me, okay? But they were watching these stars move around a central object, but they couldn't see. And these stars are moving, but they can't see what they're moving around. But it's obvious there's something there. And then from there, they could deduce what the mass of that object would have to be. And these are one of these sort of binary star or tertiary star systems where you have a star orbiting a black hole. So they had indirect evidence of these things, and they could even compute the size of that. And someone won a Nobel Prize, I guess, Halcyon theory, I forget forget the two people who won the Nobel Prize, because they were able to make predictions about the size of that black hole from that. Now we have more direct evidence of black holes, but sort of historically, people knew they were out there just indirectly by seeing how other things move around them. Okay, so these things really exist. Now that actually scared the hell out of me, because maybe coming at it from a slightly more mathematical side, I don't exist. What does that mean? Exist means they solve an equation. I'm trying to solve the equation 2x equals 4. X equals 2, a solution exists. Let's go home, right? Like, does that really exist out there? To me, I don't want to think about it, because that's kind of scary. Like, whoa, okay, this is real. So when people came across these things, like actually took direct pictures of them, that kind of freaked me out, because before it was just people playing with socks, right? It's okay because it's not serious. No, it's just it's not a serious thing. I mean, like real people do serious things. We're just fooling around playing with math, but actually they're real. So now you got to take them seriously. So here's a picture of a black hole. So historically, the person who first found the solution was someone named Schwarzschild, which ironically in German means like Schwarz means black, as you might know it. Shield, I think, like I wouldn't say shield, but it's more like coat of arms, that sense of a shield, like a shield of arms. That's sort of the word. He was actually an astronomer. So Einstein's theory, where he wrote down his Einstein's equations, was 1915. Okay, that was during World War I. So I guess Schwarzschild was already middle-aged, so probably like my age, or younger. He was the head professor of astronomy. Hey, astronomy, there you go. Good person working in astronomy. And then he was so patriotic, he said, I'm going to fight. And maybe on a Western Front, Eastern Front, flip a coin, neither is good. So he went and fought the Russians on the Eastern Front in 1916, got tuberculosis, and he came back. And that's heroism, right? How do you like that? That's real passion. Amateur astronomers who work. Well, he might have been a professional, but they were working without caring what the outcome of his work, just for the love of the subject. Lying in a hospital bed, reading Einstein's paper. In those days, you couldn't just read it on your phone, right? Or you couldn't download it instantaneously. You had to wait for a letter. The letter arrives. You open the letter. You're so sick, someone has to open the letter for you. You can't hold a pen. You're reading this, and you found a solution of Einstein's equations. The simplest one, because it was sort of spherically symmetric. And it turned out that solution described what we now call the Schwarzschild black hole. So ironically, his name was Schwarzschild, but at the time he didn't know it was a black hole. They didn't really know what that was. It was just a solution. And it had a funny problem, because if you study that solution, it's what we call a vacuum solution. So outside, vacuum means empty space, okay? And we're going to say everything is strictly symmetric. Like imagine the space outside of the sun, where the Earth lives. The sun is basically strictly symmetric. It's a sphere to all intents and purposes. So we are described, the motion of the Earth around the sun is described by Schwarzschild's solution for more than 110 years ago. Literally, his solution describes how we move around it. Students in my class can compute the trajectory of how things move, and that's how the Earth moves. That's why Mercury has a precession. All these things you could use Schwarzschild's solution to describe all these sorts of things. Now, the idea was Schwarzschild's solution only makes sense outside of a massive object. So no one really cared what happens if you go inside it, because they said, well, then we need another solution, because Einstein's equations are different, because now we have matter, and I told you curvature equals energy and matter. So the equation kind of changes when you get inside the star. So who cares? Don't worry about it. So no one really took seriously what would happen if the star collapsed so small that Schwarzschild's solution would have to be trusted even like everywhere outside of it. Imagine we got shrunk all the way down to a point. Then I need to trust Schwarzschild's solution everywhere. So it took about 40 years for people to actually take Schwarzschild's solution seriously. And they just said, wow, whatever. Some weird thing. It describes the outside, but it looks something weird happens in the middle, like there's a singularity, but forget it. Because we don't need, we can't trust the solution anyways. It's just some weird mathematical thing. And it describes the outside. And this region, which there's a funny thing I'll try to explain in a second. It's the region from which light can escape. I'll draw a picture in a second of sort of what that means. But that region, as you guys may have heard, is called the event horizon. So horizon is something very simple. We all understand. You look in the distance, there's the horizon. You can't see beyond it. Okay, so similarly with the black hole, if you're sort of looking at it, there's a region and you can't see through it. You can't see past it. Because nothing is escaping from it to hit your eyes, to hit your measurement device. So you know that you're seeing it. God, I talk too much. Okay, I gotta move on. So what happens if you fall into a black hole? This is the famous kind of idea that I want to roughly get the idea so that you'd understand. So what is this event horizon? Well, it's a region out of which light can't escape. So the gravity is getting stronger and stronger, and at this exact boundary region, which has the shape of a sphere, the light tries to get up, but it gets sucked back in. That's roughly what's happening. And if you're inside that region, you can never get out. So the black hole event horizon is kind of that boundary region where light can't escape, but doesn't fall in its exact boundary. It's sort of marginal. It's right on the edge, right? So suppose you've got this astronaut, he's attached to the rope, you and your buddy, I don't know, Buzz Aldrin or Neil Armstrong, or whoever it is, well, no, those guys, they're real heroes, those people. I'm trying to think of someone you don't like who's a real macho guy or something, like he wants to be the first one. And so you want to be famous in the history of humanity, and you flipped a coin and it turned out that they won it. So okay, he's the one who gets to go down, and you're going to be flying the ship. No one's going to remember your name, right? Who remembers I don't even know the name. Who was the guy in Apollo, the one on the moon, who was actually in the spaceship, who made sure they got off? Michael Johnson or Michael? Yes, Michael Collins. That's a real hero. I thought, how did that guy do that? If you're just off by a little bit, I'm always going to believe this conspiracy theorists. How could you be so perfect that they fly off the surface of the moon and then docks with the ship and they get back home? Walking on the moon is no big deal. I think about Michael Collins up there. That's the magic. Imagine, it's like me throwing a baseball and I have to hit exactly. I don't know. It seems crazy you can do that. Maybe you guys understand that better than me because you understand this dynamics and mechanics. But to me, that's magic. That you can't even throw a dart and hit a dartboard. How spaceship, two guys on the surface of the moon, just perfectly dock as we orbit around the moon, and then we turn on the thrusters and go back to Earth. That's magic, right? So anyway, that's why Michael Collins thinks. So you're Michael Collins in the ship, and this guy, some macho guy, says, okay, I'm going in. Like, okay, fine, you're going to be in the history books. No one's going to remember my name, whatever. That's the way it's going to go. So then you say, he's going in, and then you say, well, if you really want to remember history, you want to be the first person to actually fell in. And he's like, well, I don't think so. I want to come back, tell a story. I want the glory. I want to come back and you walk and they're waving the flags and ticker tape parade or whatever. That's going to be awesome. And you say, well, I don't think so. I think it'd be a better story if we just cut that rope and you fall in, and, that'll be amazing. And I'll tell your folks about it, tell your friends, and they'll be awesome. And what do you want your last words? We got 2,000 days to travel back to Earth. So I'll write a really awesome last words that you said, epic words. I'll read Marcus Aurelius. It'll be awesome. And I'll make some great, it'll be like Greek tragedy. And it'll be awesome. Some great story, whatever. It's going to be great. And I'll make it up. And he says, I don't want to do it. Yeah, we'll do it. Boom, cut it. And then he falls in. And then you get to watch him fall in, right? And he gets the glory. No one remember you, but at least, you have to suffer for it a bit. You got to suffer. Everything you got to suffer for it to get anything good, I think, in the world. So you fall in. Now, the thing is, here's what's really weird, is that you will never see the astronaut fall in. Because in order for you to see the astronaut fall in, a light signal, or maybe his cries of fear or screaming of pain or anger, why did you do this to me? I hate you. The last signal he sends you, that message, and whatever, the light field, what's that code called? It tips you. Yeah, Morse code. He's saying, I hate you in Morse code. And light signal, like this. He's saying you will never get that signal. You'll never feel his rage, right? Because those signals can never reach you because they're stuck on the black hole. As he fell in, those signals can never reach your eye. So you'll never see them fall and it just stops. You'll just see him like this, or I don't know, maybe he's doing something with his fingers at you. He's shaking his fist at you. I hate you. And he's falling in, and that'll be your last image of him, shaking his fist at you as you fly in. Because you would never see him fall in. But what would it be to him? So this is why it's relativity. So Einstein's theory of relativity tells you how things are related. And at this point, Einstein's theory says, well, from your point of view, you don't see him fall in. But from his point of view, you just fall in, nothing happens. Actually, if you go through the black hole, nothing specific really happens to you. You just feel what you call tidal forces. Okay, so let's go. If you look at my picture here, this is the famous spaghetti picture. So if you believe the spaghetti picture, this is sort of like the head of the astronaut as he falls in, and this is his feet. So as he falls in, they're going to start to either stretch or get squished together. In my picture here, they're actually getting stretched. That's slightly off. It's sort of the curvature is a different sign, but forget that. So basically, the force that he feels on his feet will be sort of like a differential, stronger force that he feels on his head. That's called a tidal force. Yeah, I don't understand any of this. Okay, go. Tidal force out. It's how the moon causes tides. That's gravity. So that's like real Newtonian gravity and stuff. I just do like highly idealized, unrealistic gravitational systems. But apparently, there's things called tides, and the moon causes them. And that's an example of a tidal force, a differential force, because it's pulling on sort of one side of the ocean more than the other, right? So there's a relative force between two ends. So here, there's a relative spaghettification force on your feet pulling more than your head, and that's what causes you to stretch out and turn into uncooked spaghetti, as it looks like here. Good, so here's the crazy picture of what's going on. I don't like doing this, but hey, you're here, so what the hell? I'll draw the ugly picture so you see what's going on. So there's the surface of the star at the bottom. That's a black line, okay? So it's moving. So I want you to imagine time is moving up in this picture. And what happens is eventually that star is going to start shrinking because it's collapsing under its own weight. Let's say it's really heavy and it starts to shrink. So that green line is a beam of light which leaves the origin, center of the star, flies and escapes. So what a black hole is, the idea is that eventually the gravity gets so strong, so the light rays, instead of going out, they kind of start bending in. And eventually they'll actually start, like once the gravity gets so strong, they're actually going to start to focus inwards and hit that singularity r equals 0, that singularity place where the equations break down. But the black hole event horizon is that blue curve. So it's the exact part where the light rays aren't sort of strong enough to get out, but the gravity is not strong enough so they can't escape. They won't be crawled in, they won't be dragged in, but they can't escape. They're right on the boundary. That's another way to think of the event horizon. It's the boundary region where light neither is trapped nor escapes. Okay, now I'm going to draw even a worse picture. This is even sicker. But you're here, so I thought I'd hit you with it. This is what's called a Penrose diagram. So some of you know Roger Penrose, still alive amazingly, in his late 80s, and still sharp as a tack. You can see him on YouTube on various crisis of physics videos, because they seem to be very popular. There's no crisis. You ever see those things? It's just that, like, it's hard to make progress, and people want things right away, right now, right? Where's my dinner? It's 3 minutes late on my app or whatever. So, things take time, so we should be more patient. I'm sorry. So, there's all this crisis talk. It's not the end of the world. This picture is another image of a black hole that we use. It's called the Penrose diagram. Okay. Sorry, Carter Penrose diagram. And in this picture, I want you to think of light rays move at 45-degree lines outwards, okay? So the outward line, that outward line in the black, that says kind of infinity or in the far future, that's where we live, far away from the black hole. We're just having a great time, and we're looking at it. So a light ray moving at 45 degrees in that picture can escape. But what I want you to see is that once you're inside the black hole even a light ray moving to the right could never get out and escape. He gets stuck and he hits that squiggly line. That's the singularity. So these are all pictures sort of drawing the idea of what it means to be trapped. So that kind of white line that says horizon, that's the boundary. So if I'm a light ray, just do it in your head, draw a little 45-degree line. You'll see that I can't get out if I'm inside that white line. If I'm outside, I can get to infinity and escape and tell my story, right? The other person, once he's in there, can't get out. And that's the idea of a black hole. This is something else that I want to tell you this. Sometimes a black hole, singularity and Schwarzschild solution, it's not a place. It's not like this building, University of Mississauga, and this talk is really boring. I'll just walk around and I'll get a hot talk and get the hell out of here, right? So I could move around it. The singularity, I could just dodge around and go on with my life. But that's not how it works. The problem is that singularity in the black hole where everything gets scratched in, it's not a place, it's a moment in time, okay? So avoiding it is like saying, I'm going to avoid 9 o'clock. Well, sorry, buddy, it's good. Okay, it's 9 already, I can't avoid it. You see, you can't avoid a moment in time. At least we can't, like things that move on causal trajectories. You can't avoid a moment in time. You're going to get there. Maybe we'll all be disintegrated to pieces and dust, but whatever makes you up is going to hit 9 p.m. or 10 p.m. or whatever it is. You can't escape the test by walking around it. So anyway, I got to move on. So yes. So anyway, I want to talk, the last thing I want to say, why black holes are simple. So it turns out black holes that are sort of stationary or not changing in time there's a beautiful set of results. And I want to point out someone named Werner Israel. Werner Israel was a German born. He lived in South Africa, and then he moved on to Canada. He was at the University of Alberta. So Werner Israel, Stephen Hawking, and other people contributed to this theory, the theory of equilibrium black holes. It turns out mathematically they're easier to describe. Okay, so moving on there. Yeah, I'm not going to worry about that so much. Let me just state this famous theorem. It's called the No-Hair theorem. And the No-Hair theorem says that a black hole is characterized just by a few number of parameters. Its mass, let's say its charge, or how fast it's spinning. Let's just say M and J. So if you know how heavy it is, and you know how fast it's spinning, its angular momentum, you know everything about it. Okay? A lot different than humans. If you know my weight, then you know how tall I am or something, you probably can't tell much else about me. Hopefully not, because we're all individuals. Black holes are not like that. In general relativity, you just need these two things that know everything. So that's really cool if you're someone like me, like on the mathematical side. Good, they're simple. It's easy to study. But the problem is, when a black hole is formed, you can imagine all the crazy ways it was formed. You wait a long time, it settles down, and then I only have two pieces of information. So what happened to all the information that fell in? How was it formed? Maybe it was like this star fell in. Maybe it was that star. Maybe someone threw an encyclopedia in there. I don't know. All these different things that went inside it, you lose that information. Okay, so classically, this isn't a big deal, but it turns out quantum mechanically it is. This is some crazy stuff. I should mention it. Basically, black holes behave like a thermodynamic system. So you can show that in the 19th century, when people were trying to understand thermodynamics, they realized you just need a few parameters to understand a very complicated system, like a box of gas particles. You just need mass, temperature, volume, pressure. You guys have seen some of these things. And you can describe in a simple way how a system should behave, even though you don't know what the heck is going on with all the individual particles because it's too complicated. That's thermodynamics, okay? And it turns out black holes, you can prove these nice results that show they're described in a thermodynamic way. So they're in a very simple way. But then, okay, I want to move on to gravitational waves. I want to get away from that. I want to talk about where Hawking comes in. Hawking then showed using quantum mechanics, something sick happens, that black holes aren't really black. So they actually radiate energy. And they're radiating at a temperature. Now, you have to understand, classically, that can't happen. I just told you nothing escapes a black hole. So, but Hawking showed if you use quantum mechanics kind of with general relativity together, then it turns out in 1974, you wrote a famous paper and you showed that it actually radiates, just like, like your stove when it's really hot, it kind of turns red. Just like those things, the halogen light or whatever it is, and those light things are turning yellow. They radiate particles. And the temperature is really low, so you don't know what these symbols mean. But see in that T form, there's like a little H with a line through it. So that symbol is called Planck's constant. Okay, really, really small number. You might as well be zero. So black holes are radiating, but their temperature is really cold, like much colder than anything outside that we're going to see. Like basically 0 Kelvin, negative 270 degrees Celsius. We're not going to feel it, but it's not zero. And that's a very interesting fact, okay? So the last thing I'll say is, why are black holes complicated? I explained why they're simple. So why are they complicated? Well, they're complicated because in quantum mechanics, there's an idea that information can't be destroyed. So how could I explain this in a simple way? Well, I probably can't. So why am I even trying? But I do, because I don't want to rip you guys off. You want to understand what entropy and what all this information is. You've probably heard of what entropy is. So entropy is a way of measuring what I don't know about a system. That isn't disorder or confusion or whatever. It just means what I don't know about a system. So you have a thermodynamic system. It's got some energy. It's got a volume and a pressure. Okay. So I know three things about it. But I don't know all like the little bits of details, what the little individual particles are doing, how fast they're moving. I have no idea what that is. So that's what entropy is. It's kind of a measure of the amount of information that we don't understand about a system. Okay, so you have low entropy states, high entropy states. The more, in a sense, disorder, more complicated they are, the more entropy they have. And there's a rule called the second law of thermodynamics in physics, which says that systems want to be in a more disordered state. Disorder isn't the right word. It's more like, because it makes it sound like it's a messy room or something. It's not like that. It's more like it wants to explore the largest amount of like possibilities it can get. All things being equal, a system wants to be in a sort of a set of states where it can have the most number of possible ways of being with that energy, something like that. Okay, so it wants to take on lots of different configurations. Okay, so this is all seems really confusing. Well, the whole point of statistical mechanics or quantum mechanics is to come up with a way to describe all these thermodynamic rules in a quantum mechanical way, in a rigorous way. Right? So that's what people have worked out in the 19th century. People like Boltzmann and Maxwell and Planck and all these people, and Einstein played a role in all these things. So I want to give you a little example of what entropy is before I get into what the entropy paradox of a black hole is. So here's 64 red dots. Okay, 64 red dots. And I drew them all on my tablet and filled them in. I did that. That was really stupid. There's probably some way of doing this quicker, but I'm kind of down with it. But I drew 64 circles and filled them in. And I copied and pasted the rows. I'm not that dumb. So there's one arrangement where all of them are red. Okay. Now I want you to imagine how many arrangements are there where one of them is blue. So one blue and all the rest red. Turns out there's 64 of those kind of arrangements. Because you just pick one of them to be blue. Okay. And here's another one, which is blue. So how about if I counted how many of them are there where two of them are blue and all the rest are red? You could count all of them, okay? And you get a bigger number. So what happens if I said, how many ways are there arranging these so half of them are red and half of them are blue? Big number. I can't read that. My eyesight isn't very good. My eyesight's really bad. You can count that. It's a big number, okay? So that's the number of ways of arranging it. So 32 of those 64 little marbles are blue and the other ones are turned around, so 32 of them are red. So big. So if you just ask me, hey, 32 things are blue and 32 are red. If I told you that, then you can't visualize. That's the entropy of that system. That's all the different possible ways it could have been that would give you 32 blue and 32 red, and you can't tell those apart. That's an idea what entropy is. So entropy is a way of counting all the different ways you could arrange a system so like on the outside, it looks the same. On the outside, it looks the same, but on the inside, you're like, okay, I don't know. Which one's red? Like the second from the third row or the fourth from the fifth column? Or which one's red? Which one's blue? There's all kinds of ways of arranging that. Okay. So Hawking showed that actually black holes have a huge entropy. Not a surprise. So his formula was actually the area of the horizon divided by this quantity h. And this h is really, really small. So you take a number and you divide by something small, you get a really, really big number. Okay. You take a pizza and you try to divide it into 0 pieces. You get an infinite number of pieces. Try to confuse someone with that, and then you don't have to give them the last slice of pizza. Try that trick. So black holes have a huge entropy. Is that a surprise? No, because when you see one astrophysically, you have no idea how the hell it was made, right? You have no idea. So that's all that's sort of a measure of all the stuff I don't know about it, because maybe it was formed from this kind of stuff. Maybe it was formed from that stuff. Maybe it was formed from an accreting disk of matter. Maybe it was formed by a planet that fell in. You have no idea, because all I know is the mass. Right? So the mass is like the number of red or the number of blue marbles. And the entropy is sort of like a measure of all the different ways I could have had it. So the mass was whatever, 10 billion masses of the sun or however big the black hole you're looking at is. So huge entropy, okay? So maybe that's a good place to stop. So there's these two ideas of black holes. One is this beautiful picture I tried to explain this geometric way, as I explained the work of Israel, Hawking, and others, that showed that black holes are really simple mathematically in relativity, classical general relativity. But from this quantum mechanical point of view, they're actually really complicated because no one knows what happens to that information, okay? So why is that a paradox? What's a big deal? Well, if you believe quantum mechanics, if you took your phone and you smashed it on the ground and crushed it into pieces, quantum mechanics tells you, if you put all the pieces back together, you could retrieve your friend's phone number and email addresses and all that stuff. If you burn a newspaper, pick up all the little shards and ashes and pieces of smoke, put together, you're like, now I know. Now I've got, the wanted ads or whatever. In fact, 30 years when these things existed. Okay, now I can hire someone. So these sorts of things in quantum mechanics, information is never lost. Okay, that's called unitarity. If you ever look it up. Information is not lost. So all the information that went into a black hole, it's lost because all I have is the mass and the angular momentum. Where did all that go? If I threw an encyclopedia in there, what happened to the information? My friend who I dumped in the black hole there, we cut off the rope, all of his experiences and all of his things that he ever did and stuff they did, all that is lost, all that information, right? It's gone. So where did that go? So that's the information paradox. And even to this day, people are still working on this. And if you're interested after, you can email me or I can tell you afterwards, give you some references of like what the latest work on that is and what people are trying to do. That's a big problem. Okay, so I went on a bit too long. So thank you very much for your attention, and I hope I didn't bore the heck out of you. Thanks.
Since black holes evaporate away in that slide,
Yeah.
how long would it actually take?
Yes. Okay. So I think it's a very, very long time. Now I don't have the number exactly in front of me, but it's something like 1 over the mass squared. So the heavier it is, I guess it'll evaporate. Yeah, that's right. It's a very odd thing. So black holes have a temperature, but there's something sick about it. The temperature looks like 1 over the mass. So the kind of bigger they are, the colder they are. It just kind of messed up. So it's kind of like the opposite of a normal thermodynamic object. Like the harder they are, the bigger they are, kind of the harder they are, but they're reversed. So the more energy they have, the more colder they are. So the small ones evaporate quicker. The big ones will take much longer. So the exact time scale I don't have off my head actually, but you can figure out very easily. But it'd be a very, very long time because the radiation is very slow. So the idea of like the reason why it's interesting theoretically is because you thought they were black and they wouldn't evaporate. But you don't have to really run, okay, like 20 years, it's going to be gone. Yeah, you don't have to worry about that. It's like longer than the age of the universe or something. Like several times the age of the universe. So yeah, they're not going anywhere.
So black holes might still exist when the universe fades away.
Yes. Yeah. Oh, that's a good question. If it depends what you think. You know, we think the universe is accelerating now forward. So yeah, like probably it's not going to go away. It'll just get colder and kind of depressing and empty, you know, essentially eventually empty and cold and miserable. That's probably what will happen. And things will get further away. Yeah, so the black holes will still be there.
Yeah.
Okay, for the longest time, black holes were considered theoretical. Are they considered proven now?
Oh yes, yeah. In fact, I didn't talk about this because I jumped it because I was going so slow. So in 2015, as you guys know, they found a discovery. They took 2 black holes. It's very easy to understand. One of them has got like 30 solar masses. One's got 35. They crash, and then you get a black hole which has 62 solar masses. So somewhere there's 65 minus 62. There's 3 left over. So there's 3 solar masses worth of energy left. So it turns out they were using their gravitational wave detectors. They actually found that missing energy roughly. And that's this gravitational wave. So that I would say they're directly understood. And then there's these event horizons.
Since you showed that diagram, is there any way, any place that I can read something that I can understand myself on how that works and how they can explain from the waves why they know everything that they do know? Like the size of the black holes, the distance, etc.
That's a very good question. So the question was, like, where could you go to look for how this LIGO actually worked? That's a good question because I actually looked at that just a few days ago myself. Because to me, like LIGO is again magic, right? That's something no experimentalist. So I think a good place to look for is actually the LIGO website. But if you're interested, just email me and I'll find the site for you. Because the head of sort of one of the chief spokesperson is actually someone based in UBC. Her name is Kyber. You know Kyber, I guess. So and I think on her website, I went there and she had links, but they give like a nice explanation of how this all works, how the interferometers work, and how they use general relativity to actually deduce from the data signal what the mass was and all that stuff. So there's no magic there. That's like classical physics. So yeah, that's pretty solid stuff. Yeah.
Yeah.
Okay, so black hole, event horizon, light can't escape. So the path of a light beam, if it's going at 45 degrees, is going to go back down into the black.
Well, think of it more, it goes in a straight line. Yeah, I'll show you that picture.
Yeah.
Yeah. I put that picture. Classical stuff. I know that. Okay. Yeah, here we go. That's terrible, but okay, good enough. So if you're outside of that white line of 45 degrees, you just move out to infinity. If you're inside that white line, like it's kind of like orange, the orange region, inside the white line, and I try to escape, you see, I can't get out to infinity because I'm going over 45 degrees. So the white line is the exact boundary. So if you're a light ray on the event horizon of the black hole, you don't go in, but you don't go out, you just go in a straight line.
Right, but I'm interested in special cases. I'm sitting on a black hole, amazing, and I shoot directly 90 degrees. Does it go up and slow down? It can't slow down.
It'll just stay, it won't go any further away.
Does it even move?
Yeah, so it wouldn't move. I know that sounds sick. You shine the light beam, it would just kind of stay beside you. And remember, okay, but here's the sick part. If you're moving, then you're also moving really fast because you're actually moving on your own. You're moving at the speed of light if you're on the edge of a black hole as well. So it's a bit sick, but yes. Let's say, forget all that, you're just observing, you shoot your light, it can't leave you, it won't fall in, it'll just, so you aim it outward, like that's out, fire the light beam out, and then it'll just kind of stay there. Like, hey, what's going on? So when you see the pictures of a black hole, like what you're actually seeing in this very interesting telescope, you see it's like a little red halo, and it's kind of artistic and they changed to make it visually interesting. But you're watching light rays trying to escape out, and as they accelerate outwards, they actually lose energy, they radiate away energy, kind of, and you're seeing that red light of them as they kind of fall in. That's the energy they're losing as they accelerate in. That's kind of why you see that red light around it. Yeah, but it wouldn't move. Yeah, it would be stuck. Oh, go ahead. Maybe I'll ask you. Actually, you should call.
Dr. Bendara, but you said earlier that anybody, light is traveling at the speed of light away from anybody. Like if you're on the train, beside it, and now you're saying that the person on the event horizon, the light is not moving over.
Yes.
Why would
Okay,
just
listen.
the light away?
Yeah. Yeah, that's amazing. So you actually you followed it then. Good, okay. So I try, it's amazing. People follow what I'm saying. I'm really surprised. I can't believe it actually, because I just assume no one, like, because I talk in this garbled way, incoherently. You're exactly right. So you'd say, well, yeah, I just started to myself because everything I can see to be right. Yes. So the one little catch is if you're on the black hole event horizon, you're moving on this 45-degree line. That means you're moving at the speed of light yourself. That's why when you see this, like you are light, so it wouldn't look like the light's moving because you're moving at the same speed as it is. So it's not moving with respect to you. So it's at rest. Yeah, I know that sounds dumb. So for you to be living right on the edge of the black hole, you have to be moving at the speed of yourself. Yeah, you're living on the boundary. Otherwise, you could be falling in, right? If the gravitational force is pulling you in. So if you're living, so light rays, the boundary of the black hole is defined by beams of light that don't get out. So if you are on the boundary, you yourself must be a light ray. So you're exactly right with what you're saying. The bit I kind of lied about it. The boundary means you are. Yeah, no, that's a good question. So that would be sort of material which is not quite inside it yet. Right? So remember, you're only trapped if you're inside. As long as you're outside, you don't need to be trapped. Right? So if I'm a light ray and I'm pointing outwards, as long as I'm outside that black hole horizon, I can still get out. So what you're seeing there, roughly, actually, it's out of my room, a friend of mine who knows this stuff actually quite well. You have this black hole, and if it's spinning, that creates sort of a magnetic field. And what this does is causes charged particles to shoot up. It's creating the kind of electromagnetism. There's a force which pushes up on the particles. And so charged particles will tend to flow outwards in this jet stream because it's spinning. So that's kind of what you're seeing there. So these are particles which haven't fallen in. They're just on the outside, like say a ball of like gas and dust outside the black hole. So they're being trapped in, and then they get trapped by this magnetic field, which spits them outwards. So that's the point. They're not trapped yet. So you only trap once you touch it and you go inside. Once you're outside of it, you don't necessarily have to fall in. Yeah.
David? Okay. I'm keeping an eye on who's racing, by the way. So you'll get to start.
You're tracking. So somebody who's at the event horizon, from our time perspective, they would freeze.
Yes.
Because of time dilation and that's interpreted. Would they, from the person in that reference frame, if they didn't actually get tidally torn apart, would their time still flow?
Yep, their time would just tick, tick, tick. They just walk through like no big deal. Yeah. Yeah, so that's a bit weird. But if you believe this principle of equivalence, nothing special should happen there because you're just a freely falling observer, just falling through the black hole. And you can even compute using these equations, like you can compute how much force someone would feel going through there. And the bigger the black hole, it turns out the weaker the force. The bigger it is, the less of a force field. And so on a big black hole, you can just walk through like no big deal. Yeah. You feel a force like I feel a force. So what is getting out? So the idea is, so Hawking shows it is radiating quantum mechanically. So really small stuff is getting out. Now, eventually, as someone else mentioned to me, as the black hole radiates energy, it loses energy, so it's actually going to shrink. So the question was, eventually all you're left with is this radiation. And in terms of radiation that's very disordered, you can't get much from it. You know, when I see a light, all I see is it blue or red. So I can kind of deduce the temperature of the source that emitted the radiation, but that's all I know. So a lot of information is lost. So what people are trying to work out now is maybe Hawking's calculation wasn't correct. Exactly it. The radiation isn't perfectly thermal. It contains this extra information. If you look more closely, maybe you can see that. Like there's something that Hawking missed. I'm not saying he's stupid. It just like he made some approximation that this is this extra kernel of information, and you can deduce it. So the analogy is like you burn the newspaper, but Hawking says, well, all you're left with is dust. But maybe if you did it more carefully, you could take the pieces of paper, get them back together, and use the newspaper. Yeah, that's the idea.
Yes.
Yeah, I mean, first, answer to Chris's question, you agree that the light is slowed down in the black hole. Does that mean that Einstein's theories do not work inside the black hole?
Ah.
In which case, there's a whole new science waiting for us?
Oh, no. Okay, that's the cool thing. So once you get inside, yeah, light waves are always moving at the speed of light. So yeah, everything works the same on the inside. Yeah, the only difference is they can't get out to tell us about it. But really on the inside, nothing particularly weird is happening. Except for you have this, you can't avoid the singularity because it's in your future. So you're going to hit it. So think of it more like the singularity is like a moment in time, as I said before. So it's like 5 o'clock. So there's nothing weird goes on. Just at 5 o'clock, you're going to hit this thing and disappear. So sort of from the point of view of accounting, it's kind of bad because we don't know where the money went. It kind of just disappeared. So to physicists, it's not good because they like to know what happens when you hit something. It said general theory just doesn't tell you anything anymore. This is you hit this and I don't know what happens. But apart from hitting that, as long as you're inside, nothing really weird happens to you. Yeah. Apart from these forces. So you'd say it shouldn't have a high degree because that's just the way it is.
Well, if everything is indistinguishable, then the sense of the complexity that you talked about, the possibility of
I see. There's no such thing as red or blue. They're all the same anyway.
The elements are essentially the same.
Yeah.
Where's the entropy?
So maybe they have, in a sense, it's zero entropy because everything is there's just one state. Everything is red and that's it. Yeah, I could see that. I guess I could see that. Yeah, I never really thought about that before, but I guess in quantum mechanics that shouldn't happen. You should be able to tell things apart. Yeah. So the idea is if you set the initial conditions in it, you should be able to retroactively figure out what went in. So people who believe quantum mechanics before they believe relativity, like most physicists, not me, but people who do quantum mechanics, that's something they really believe in. That's like a fundamental part of the structure of quantum mechanics. That you can always turn the clock back. It's reversible, right? So they don't like the idea of what you're saying. So even if everything is a blob now, they'd say, yeah, but if I turn the clock back, I should be able to work out what it was before they all kind of became indistinguishable.
But quantum mechanics says you can't turn the clock back. Time cannot go reverse.
Yeah, well, no, yeah, well, you should be able to do it. In principle, like the equations tell you can turn the clock back. That's what mathematically it says that. But like equations, like Schrödinger's equation, it works backwards. You send t to minus t, you can trace back. Yeah, it's not like a heat equation or something. Well, you can't go backwards. So if you know what happened now, you should be able to predict what happened in the past. Even in quantum mechanics, you can do that. Yeah. Well, that's a good point, though. Actually, I don't think about this stuff too much because I'm not my pay grade. I'm more of a bread and butter kind of gravity guy. Studying solutions. Just trying to dig holes and working hard at these things.
Okay, I have one.
Oh.
So our galaxy has a supermassive black hole in the center of it.
Yes.
And so do other galaxies. So what do we have an estimate how what made those? We know it's stars, but what how old they are, or will they exist in perpetuality? Like, do we have a sense?
Yeah, so the objects you're talking about, these supermassive black holes are at the center most galaxies, I think now is accepted by astrophysicists, they exist. Ours, I forget what it's called, you guys know Sagittarius. A-star. So this is what, 26,000 light years from us? 4 million solar masses. The other one they took a picture was M87. You guys, that's much further away, like 1 point something billion light years away. And that, something far away, you wouldn't see that, even you guys would totally see that one. And that, maybe you need help to see that. And that one is 5 billion solar masses. The black hole at the center of M87. So these things are all supermassive. So this is actually a big question in black hole physics, astrophysics, understanding how they got that big. If they're like the basic model we have of black holes, astrophysical ones, tell us that there's a certain limit on how big they can get. So it seems like these, in a sense, they're too big for how old the universe is. They got big too fast. So like an open question in black holes is, how do supermassive black holes, how they get so big, how do they exist now? Because they didn't exist forever, but it seems like they may have existed from the beginning of the universe, 13 billion years ago, 13.5. And so, and even then, it doesn't, still we can't explain how they get as big as they do now. Like my idea was you got a galaxy, so there's a lot of stuff for the black hole to eat, right? So it makes sense they get big, but it turns out if you study this properly, you find even that wouldn't explain how they got this big. And they're really big. Yeah, so that's a really interesting open question. Oh, because they can see it. Because, yeah, as we found, it's very far away. I think it was like 1.5 million light years. I don't know, billions. What the hell does it make a difference? Far away, really far away. But it's 5 billion solar masses, that guy, or 6 billion, give or take a billion, right? So it's really big. So you can see it with, super awesome telescopes. The one at the center of our galaxy, like the Sagittarius A-star, that guy, like 26,000 light years away, that one is also of a similar brightness, even though it's only 4 million solar masses, so like a few orders of magnitude smaller. It's so much closer to us that it appears at the same brightness. So that's why they were the two best ones they could image. That's the only reason why. It's like there's nothing special about it. Maybe the one in the Milky Way, that's the closest one, so it's kind of cool, right? One thing I actually want to tell you, I was reading about this on one of these LIGO sites. The sensitivity they needed to study gravitational waves was something like being able to judge the distance to Andromeda. It's like 4.2 million light years, something like that, to the size of a human hair. That's how sensitive you have to be. Like 1/10,000 the size of a proton. Right? Just like you can't even imagine it, how sensitive the devices they use to discover gravitational waves. And similarly, the technology they use to do the Event Horizon Telescope, there's someone in Waterloo's, maybe body records professor there, who's deeply involved in that project. He was telling me how sensitive the equipment is to do that. The cool thing is, I didn't ask you what the hell's the point of this. And there is a point, because probably in 10 years, they'll be using that technology, and hopefully, not the physicists, but someone will say, hey, I can make money out of this to make better phones or something. So, and maybe some of that will even trickle down to humble astronomers taking pictures, like doing really cool stuff in your garage or something on a clear night. So it will trickle down eventually.
I've never seen it or heard it mention the Event Horizon. Does it have a thickness? And if so, is it dependent on the size of the black hole?
It is. So hey, I get to be an equation guy. Look at this. Well, I like this stuff, because this is an equation, so I can hide behind it. There's anything I can do, it's run away from physics by hiding the equation. So it's something which has a size, and the size of it is roughly, forget all the constants, it's something like, it's the size of the black holes, it's the mass. So the size of the Event Horizon, think of it like a sphere, has a radius, and the radius of that sphere is roughly equal to the mass.
Great, okay, that's what I'm talking about, not the actual circumference.
Yep.
The thickness of the actual.
Now the actual thickness. So here's where it gets a bit, so it's idealized, so it's like the skin of an apple. It's infinitely thin. So when you think about this sort of mathematically, it doesn't really have a thickness. It's like a volume, and this is its boundary. So it's kind of like infinitely thin. It wouldn't have a thickness.
Regardless of the size of the black hole.
Yes, yeah.
Okay.
It's like really like the skin.
I've never seen that anywhere mentioned.
Oh, okay. Well, maybe people, the thing is, mathematicians who often write this, so physicists, we just take that for granted. So when we think of the boundary of anything, like the boundary of like this, or the boundary of this water bottle, when we say the object is the inside and the boundary is just like the skin of the outside, we just kind of, it's like one dimension thinner than the stuff. The inside's wide, the outside's an area. So without thinking, when we say boundary, we just mean it doesn't really have a thickness. Yeah. So that's a funny thing. I never thought about that, but yeah, it's sort of when you say it, like, yeah, it doesn't have a thickness. It could be this thick, right? Like an orange rind or something. But it's more like an apple skin or a grape skin. Something,